Okay, so now we can talk about a second type of ensemble learning called boosting. Okay, and this is kind of similar to bagging in the sense that we look for a committee or like a classification to be made from a group of models, but the way we add the models is sequential, and it's a little bit different from before. So before I define boosting and kind of derive the algorithm, I just want to talk quickly about a weighted loss function. Okay, so up to this point, we've kind of seen loss functions that look like this. So this could be, your true data point and the predicted data point, and the loss function, for example, this is squared error loss, is, sorry, there shouldn't be an I here, is just the squared difference. Okay, so this is just the mean squared error. Okay, but suppose you had the following scenario where you're doing, let's say, well, I mean, we wouldn't use mean squared error for classification, but let's just say that you had a data set that looked like this, that was 96% in the positive class and 4% in the negative class. Okay. Now, if you have this is called an unbalanced data set. Okay, it's unbalanced obviously because, well, actually, sorry, let me change this around to positive and this to being negative. Okay, and let's think of this as cancer, like let's say lung cancer. Okay, so you have some data that tells you, that gives you some predictors about lung cancer, but only 4% of your sample is positive, and the rest of your sample is negative. Okay, so this, like, understanding how to predict cancer is really the important part of this data set. But we can really easily get a 96% accuracy rate by just predicting the majority clause. Right? Because if I just always predict negative, 96% of the time I'll be right, and that looks like a really good accuracy, right? 96% sounds really good, but the problem is we have this really unbalanced data set. So the 96% accuracy is actually like the kind of the worst case scenario. So it's like we're getting everything wrong in the positive case. Okay, so one way to remedy the situation, I mean, there's a few ways. One way to remedy it is look at weighted loss function, where we would have weights. So let's say there's 100 data points here. We would have weights W1, W2, W3, W4, all the way to W5, and then all the way to W100. And let's say that the 96 points from 5 to 100 are the negative points, and the 1 to 4 are those positive points. So you wanna basically make your algorithm or your model care more about these 4 points. So making a mistake on one of these 4 points should be really expensive, right? So one way you could do that is to have weights that are higher. Okay, and this is just a random weight I'm using, and the rest of the weights could just stay at 1. Okay, and then your loss function. So let's use the same loss function, even though this is a classification task. I'll call it LW y hat will be Wi times this. Okay, and what does the Wi do? Well, it says that for the ith point, if it's one of the first 4, or the positive points, then the loss So making a mistake, a large mistake on that point is going to be penalized more heavily, right? This is the loss function, so it counts the penalty. So for these 4 points, making a mistake, the penalty is going to be quite high, and the model cares less about these guys. In fact, it cares 100 times more about making the right classification on point 1 than it does on point 5. Now, this is just an arbitrary weighting scheme that I came up with, but hopefully it just kind of describes the idea of why it could remedy this situation. And usually what you'll see is that we want our weight vector, we want the sum of the weights to be 1, right? This is pretty common, just to have the weights normalized. It's not really necessary in a lot of cases, but we'll usually normalize it. So in this case, our unnormalized vector, let's say, is 100. Okay, so to normalize it, we would divide, so this is the normalized version, we would divide 100 here by the sum of all the points. So that's 96 plus 400. And then 1 over 496. Okay, so this idea from going from here to here is just normalizing it, like standardizing it such that the sum of the weights is equal to 1. Okay, and this idea of weighted loss function is going to be pretty crucial in boosting. And in particular, today I'm going to be talking about kind of one of the most famous called AdaBoost, which is this Ada is adaptive boosting. Okay. All right. So we need weighted loss functions to describe this algorithm. The idea behind AdaBoost is we want to come up with a classifier. So this is going to be for binary classification in this particular example that I'm talking about, but obviously you can extend this idea. We're going to have an idea, well, the basic idea is that we have we're going to be converting a weak learner into a strong learner. Okay, and what I mean by weak learner is a basic model that achieves an error of, well, basically it has to be, on a binary classification task, it has to be slightly better than guessing, right? So guessing means I would just get a new observation and I would guess one of the clauses. And so the error rate from guessing would just be 50%. So this has to be slightly better than 50%. So it would be, the error would be 50% minus delta, where delta is some small number. Okay, that's a weak learner. So a weak learner is any really basic model that's slightly better, just slightly better than just guessing. And a strong learner, well, just from the name, a strong learner hopefully is an algorithm that is able to get an error rate that's much lower than 50%. Okay, so we want to, the idea is basically that how do we achieve good performance on prediction tasks? Okay, well, the traditional way is, okay, let's say you have a linear regression. To get really good performance, you might do like feature construction. You might come up with a lot of good features and add them to your model, and then try to build a strong learner by accounting for more and more variation in your response by looking at more and more variables. Okay, or you could build a neural network, and this is a complex. It has a complex architecture. But if you add more and more layers and you add more and more data, then you might get a strong learner. The idea of boosting is completely different. It says, forget about trying to construct this really complex model. Just take simple models. So put simple models together in a smart way. Okay, and it's the idea that you can have a lot of simple models take the average decision, right? Like let them all vote, and then the average decision is the final decision. So instead of relying on one, so this is kind of like the one expert. In boosting, we have a committee of, I guess here you have one expert versus a committee of slightly, I don't want to call them experts because this is just slightly better than guessing, but it's a committee of okay, because here you have an expert that just like a single model that's kind of learned everything, tried to figure out all the different aspects of the data, and now is giving you predictions. Whereas this idea is kind of the wisdom of crowds, right? You look at a large group of models, you take the majority vote in a smart way. Okay, and the idea of boosting, I mean, if you think about it, so let's say you have this really complicated function that looks like this, right? And you only have some building blocks, which are either horizontal lines or vertical lines. Okay, and I want to combine these two building blocks in a way such that I can approximate this really complex blue function. And the idea behind boosting is kind of this, right? Because I can basically take little incremental steps. Okay, and maybe my drawing is not great, but hopefully you can see that I can get a pretty good approximation by just using these really simple models and taking really small increments. So I combine these models to actually be able to predict or be able to learn this complicated function. Okay, so what I'm doing here is taking little steps and just basically combining these guys like Lego to be able to learn this complicated function. Whereas in the one expert case, I would just try to fit the entire thing. So in linear regression, sorry, in a neural network, you might kind of predict the whole thing with a global function like that. Okay, I'm not saying this is a bad way of doing it. It's just that the first way almost takes more work. The second way, the boosting way, you really just have to work with really simple models. The work is in how to put them together in a smart way. Okay, so that's the idea of boosting. So let's actually define it kind of more rigorously. Okay, well, let's just say we have some samples, some data. From 1 to n, and we're looking at binary classification. So our yi can be either negative or positive 1. Our xi can be anything. It could be a vector, it could be a single number. It doesn't really matter. Okay, and we are going to look at a class of weak learners. Okay, so you can just think of these as basic models. And let me call this class big H. And so what's going to be in big H is little h. These are functions that map, let me just write it like this. Okay, so what this means is that h is a function that takes an input value x, right, like our x sample here, and it predicts a number either -1 or 1, -1 or 1. Okay, so this is a function that maps from the input space to the label space -1 or 1. And big H is just a collection of all these kinds of functions. Okay, so this, for example, H could be the set of decision trees of depth 1, right? A decision tree of depth 1 just looks like this. It's a binary decision. It's not very complicated. It just looks at the entire data set and splits in one go. Okay, or it could be the H could be the it could be the set of perceptrons. Okay, so perceptrons is a linear classifier. It's pretty basic. You can have H just being the set of all possible perceptrons. Okay, the idea is that this is a really simple. It's a class of really simple models that can be trained quite quickly. Right, decision tree with depth 1 can be trained very easily, very quickly. Okay. All right. The next thing. So this derivation, by the way, is called the exponential loss derivation. And this is the way I like to think about it. It's kind of different to the lecture notes, but I think it's actually easier once you see it to derive it this way. And we're going to use a loss function, which is called the exponential loss, which takes two arguments, which is the prediction, h of xi, and the actual label yi, and it gives us e to the power of negative yi h of xi. Okay, and so if you remember, well, I'll just graph it here instead of using the grapher. If you remember the, well, hopefully you remember the exponential function. Looks like this. Okay, so this is y equals e to the power of x. This point here happens at 1. Okay. What is this saying? It says that so this is a loss function, right? So when h of xi and yi are both equal to 1, so when the classification is correct, right, then yi times h of xi is going to just be 1, right? Because if yi is -1 and h of xi is -1, -1 times -1 is just 1. And similarly, if they're both 1, it's going to be 1. So this means that e to the power of negative yi h of xi is going to be equal to e to the power of -1. Okay. In other words, it's going to be if 0 is here, it's going to be a negative number, so it's going to be a number that's small. Okay. Whereas when yi is not equal to h of xi, then they disagree. So either yi is 1 and h of xi is -1, or the other way around. But what happens is that yi times h of xi is now going to be equal to -1. So that means that exponential of negative yi h of xi is going to be e to the power of 1, which is up here. So it's a higher number. So this loss function gives us a higher value for mistakes and a lower value for not mistakes, right? That's basically the idea, and that's what a loss function should do. By the way, this is this loss function is not a good loss in practice. So don't use this loss function. I'm just going to use it here because it's got a nice way of deriving this AdaBoost algorithm, but in general, don't use it. I just wanted to illustrate that it's actually giving us the right behavior of a loss function. Okay, so we have our loss function, we have our class of weak learners, and we have our samples, and then we need our goal. So the goal of AdaBoost is to come up with a classifier, let's call it C, which contains M base classifiers or weak learners, and it's going to take an input X and it's going to predict, well, let's just say CMX is the linear combination, so alpha 1 times H1 of X plus alpha 2 H2 of X plus, and this is going to have M blocks, so it's going to be alpha M HM of X. Then the final classification is going to be the sign of CMX, right? So each one of these guys is going to be +1 or -1, right? H1 of X, H2 of X, up to H of MX, because they're all binary classifiers. The weight we assign to each classifier is this alpha 1, alpha 2. Then we add this number up, we get a number either positive or negative. If it's positive, so in other words, this sign thing is equal to +1 or -1 if Cm of X is bigger than 1, if bigger than or equal to 1, and it's -1 if it's less than, sorry, I mean to say 0. Let me make that neater. Okay, so this sign function is just the same way we deal with perceptrons and other binary classifiers, but here this CMX is a linear combination of M base classifiers. Okay, and that's the idea behind AdaBoost. So to derive the algorithm, we need to understand how do we, so questions, how do we pick H at step T? So like you're basically thinking of this as, at step 1 you pick this guy, and then at step 2 you add this guy, and you keep adding more and more for M steps. So how do we pick H at each step? And then 2, how do we pick weights alpha M, right? So how much weight should I give H2? How much weight should I give alpha H3? Okay, the one thing before we answer that question, the one thing I want to mention here, the difference between boosting and bagging, right? Because this is bagging also includes a bunch of models into kind of a combination like this. The difference here is that so let me write it again. CMX equals to alpha 1 H1X Okay, the difference is HK is trained to focus on the mistakes of HK minus 1. Again, and we're going to see an example of this, but the point is that I first get my H1, right, my first classifier. This classifier is going to make mistakes on some of the data. Then I take my H2 and I make H2 focus especially hard on the mistakes of H1. And the idea, how do we get this performance? We use weighted loss functions. Right? So if H1 makes mistakes on data points, say 1, 4, and 5, in the second round of the algorithm, H2 is going to be trained on a loss function that assigns a higher weight to those points, right? So we'll see a lot of examples of this, but that's basically the idea of boosting. The boosting is that the next person coming into the next algorithm coming into the model is kind of an expert at the mistakes of the previous model. All right, so how do we actually answer those two questions? We have these two questions here. How do we pick these guys, alpha and h, at each step? So let's answer that. The way to answer those questions is to kind of do this recursively. So assume that we are at step m minus 1, okay? Which means that we've already constructed this classifier. Okay, so we've already got these m minus 1 pieces. We know alpha 1, we know h1, all the way up to the end. So how do we go ahead and add the additional piece this piece here, alpha m h of x. Okay, so we need to know how to pick these two guys to add them to this model, and we assume that these m minus 1 pieces are already known. Okay, so we can rewrite this as c m minus 1 x plus alpha m h m x. Okay, hopefully that's clear, because the first m minus 1 pieces are just the previous model, and all we're adding to the previous model is this alpha m hm piece. Okay, and we're going to assume that the data has weights w Okay, so how do we pick alpha m and hm? Well, we have our loss function, right? So let's actually compute the loss function for this model. It's going to be the sum of, well, we're using the exponential loss, so yi cm xi, right? So this is just the classification from our boosting model on the point xi times yi. And using this expansion that I have here, I can rewrite this as e to the power of negative yi times cm minus 1 xi, e to the power of negative yi alpha m hm of x. Okay, and okay, so I'm going to call this guy w mi. Okay, and the reason I want to do that is because there's basically this thing here is fixed, right? We're trying to minimize the loss function, but the only thing that we have power to change is these two guys, alpha m and hm. Okay, so I'm going to treat this as a constant, as a fixed thing, and I'm going to call it a weight, wim. Now the goal is to pick alpha m and hm, so we want to pick them to minimize the loss function. So we want to pick alpha m and hm to solve this optimization problem. And let me rewrite it here using our new notation. And let me write it as alpha m yi h m of xi. Okay. Now, how do we do any optimization on this? Well, the best thing to do is to simplify it. There are two cases that can happen. right? We're summing over the entire data set. There's two cases, case 1 and case 2. In case 1, yi is equal to hi. So hi, by the way, is just hm of xi, but I'm going to use hi to save myself having to write out the whole thing every time. And the second scenario is that yi is not equal to hi. So in the first case, where the classifier is predicting is classifying correctly, and in the second case, it's making a mistake. All right, so I can rewrite the summation. I can break it up over the two pieces, right? So the first piece is I such that yi equals to hi, and in this case we have wim, and this exponential term. Well, if yi and hi are equal, then this is just equal to 1, right? And so we get e to the power of negative alpha m here. And the second piece of the summation is the I such that the yi is not equal to hi. So here we're making mistakes. And again, we get the weight, but now we get multiplied by e to the power of positive alpha. So the loss, this number here is bigger when we're making a mistake, right? Versus here when we're not making a mistake. Because e to the power of a positive number, alpha m, is bigger than when it's a negative number, right? So we can see that we always want to be on this side of the exponential function, not on this side. Sorry, we want to be on the left side, not the right side, because we want to minimize loss, and being on the left side gives us a much smaller loss than the right side. Okay, so let's simplify this even further. Note that e to the power of negative alpha m doesn't have any i's in it, so we can actually take it outside. And we're left with this weighted, the sum of the weights on the points that we're not making a mistake on. And here we can take the alpha m outside as well. Okay, and this is what we get. Now, we want to pick alpha m and hm. And by the way, I'm assuming alpha m has to be positive, greater than 0. And that's why this negative alpha m is always a negative number, and e to the power of, why negative alpha m is always a negative number, and alpha m is a positive number. Okay. All right. So how do I pick hm first? And I'm going to kind of prove this without doing any calculus. We're just going to look at this thing, and we're going to see that there's two scenarios. The first scenario is the classifier makes no mistake, so these data points. And the second scenario is that the classifier does make a mistake, which is these data points. And every time we make a mistake, we add this big number here, e to the power of alpha m. And when we don't make a mistake, we add this small number. So to minimize, right, because we're trying to minimize the loss, the best thing to do is to try to minimize the number of mistakes. But the catch is that here this is a weighted mistake. So again, this is just like the weighted loss function I talked about earlier. So what we want to do is we pick hm to minimize the weighted the weighted classification error, which is just this summation, I such that I not equal to hi of the weights. So if we make this number really small, then all the points are going to be in this summation, and we're going to be adding this really small number, e to the power of negative alpha m. So the best case scenario is where this sum is zero mistakes, in which case the sum, the e to the power of alpha m term doesn't play a role at all, and we minimize the loss function. Okay, so we pick hm to minimize this misclassification rate, and basically this is just the normal way of training any model. We want to minimize the error. It's the only difference is that now we're giving each data point a weight, which is equal to this WIM, which we'll talk more about in a minute. So that's how you pick hm. The second part is how do you pick alpha m. Okay, so let's rewrite this loss function here. And how do we pick alpha m? So we want to do arg min alpha m. Well, we just use calculus, right? So let's just differentiate the loss function with respect to alpha m. from the first exponential, we'll just get a negative e to the power of alpha m times the sum hi equals to yi. And then from the second one, this differentiating this exponential just gives us itself I such that hi not equal to yi times this, and then to minimize, we make it equal to 0. And then we try to solve for alpha m. So if I multiply both sides by e to the power of alpha m, so if I times this side by e alpha m and this side by e alpha m, what I'll get is okay, so this, sorry, this should be a negative here. And when I multiply by e alpha m, right, what happens to this guy? Well, e to the power of negative alpha m times e to the power of alpha m is e to the power of negative alpha m plus alpha m, which is e to the power of 0, which is equal to 1. Okay, that's what's happening here. So the first summation loses its exponential term. The second summation gets alpha m plus alpha m, so it gets 2 alpha m hi not equal to yi equals to 0. Okay, and when I multiply 0 by e to the power of alpha m, it's just 0. So that's why I can do that, multiply both sides. Now I want to solve for alpha m, and hopefully you can see it's going to be pretty straightforward. I'm just going to move this summation to the other side, and I'll get e to the power of 2 alpha m equals to the ratio and I should stay consistent. I should put I such that hi not equals to yi. Okay, so I'm just moving I'm moving this guy to the other side, and then I'm dividing by this guy, and I get this expression. If I take the logarithm of both sides and then divide by 2, I'll get alpha m is equal to half times the natural logarithm of the ratio of these are the ratio of good points, so the proportion, sorry, the weighted sum of points where I'm not making a mistake divided by the points where I am making a mistake. Okay, now I'm going to simplify this expression by dividing. So I can divide by a number here and divide by a number here, right? It doesn't change the value inside. If I divide the numerator and denominator, they will cancel out. So what I'm going to divide by is this thing, and I'll explain it in a minute. And I know this looks like it's getting messy, but hopefully it's pretty straightforward once I explain it. I'm going to divide by this sum. This is the sum over all data points, regardless of whether there's a mistake or not, of the weights. And I'm going to do the same thing on the bottom. Okay, and the reason I'm doing this is now what we have, so what we have is a weighted average. Okay, so how do you do averages? Like, let's say I have the number 1, 2. Let's say I have this vector 1, 2, 3. The average is 1 over 3 times 1 plus 2 plus 3, right? What if I have the same numbers 1, 2, 3, but I have a weight w, which I want to give the first point, I want to give it a weight of 2, and then I want to give the middle point a weight of 1, and the last point I want to give it a weight of 10. So for some reason I care a lot more about this last number. Then the weighted average is 2 times 1 plus, so I multiply the weight by the actual point, plus 1 times 2 plus 10 times 3, but then I divide by the sum of the points, 2 plus 1 plus 10. So the weighted average is wi xi divided by the sum of the wi. Okay, and this is just the way you take a weighted average. So all I'm doing here is dividing both numerator and denominator by the sum of the weights. And the reason I want to do this is because it lets me work with the this quantity here. Okay, and let me introduce what this epsilon m is. So this is the summation of the mistakes, the weighted mistakes at iteration n divided by the total sum of weights. Okay, so this is the weighted classification error proportion. Okay, so it gives me a proportion rather than just the sum of the weights. It's kind of like taking an average, a weighted average of the error. Okay, that's all it is. So again, just to reiterate, I choose my my alpha m to be this quantity here. Okay, and so let me just kind of explain why this thing makes sense. Well, remember, alpha m is the weight of the classifier hm, and hm achieves error rate of this guy, right? Because it's minimizing, it's minimizing the this thing here, right? Which is, if you divide it by the total sum of weights, is the error rate. So if you divide the error rate, or if you minimize the error rate, or if you minimize this, it's the same thing, because remember, we can always divide this by some kind of constant. Okay, so hm achieves an error rate of epsilon m, and alpha weight is the weight associated to hm. So this just says that the weight should be is higher if and you can rewrite this as this, right? And so we can see that as epsilon m is lower, right? If I divide by a smaller number, this ratio is going to be bigger, and so logarithm of a bigger number is going to be bigger. So in other words, alpha m is high if hm is a good classifier, right? In other words, it achieves a lower error rate. Okay, so that's kind of the intuition. This kind of makes sense. So now we have a way of picking alpha m and hm. So let me just go back to one step before, which I kind of skipped over, which is where I defined this weight function. So I just kind of said this, and it was a little bit out of nowhere, but I defined this quantity here to be my weight. And you can see that the weight is going to be changing every iteration, right? Because it's based on the current model, or the previous model m-1. So the weights for iteration m are based on the previous model m-1, right? So I can rewrite this well, I can just, we want to basically also write out the updates for the weights, okay, because they're changing from step to step. So what is the weight again? It's going to be e to the power of negative yi c m minus 1 xi, right? Now, we can use the same trick to expand this out because we know cm minus 1 xi is just the previous model, cm minus 2, plus, well, in m minus 1, right, we added alpha m minus 1 h m minus 1 xi. Okay, and then expanding that out, we get e yi. Okay, and again, this guy, right, is just, if you look at the functional form, the weight im is just exponential negative yi cm minus 1. So this here is just going to be the weight of I at m minus 1 times e to the power negative. Right, so we see we have this recursive relationship where the weight at time m is equal to the weight at time m minus 1 times this update factor here. Okay, so let's break this down into the two cases, whether we make mistakes or we don't make mistakes. So if yi equals to, and let me write it out now, h m minus 1 of xi, then the weight update is the previous weight times e to the power of negative alpha m minus 1, and yih m minus 1 xi just goes to 1. And we now know what alpha m minus 1 is, right? We already derived it, so this is w I m minus 1 e to the power of negative half log, natural logarithm of epsilon, 1 minus epsilon m minus 1 over epsilon m minus 1, right? Because this is the alpha m minus 1, so it's a function of epsilon m minus 1. Now I can simplify this by taking, so this is a logarithm, I can take the negative half up to the top, so I get e to the power of log 1 minus m minus 1 over m epsilon m minus 1 to the power of negative half, and exponential to the logarithm just cancels out, so we get wi m minus 1. Now the negative means I can switch the fraction over, and the half is just a square root, so I'll get square root epsilon m minus 1 over 1 minus epsilon m minus 1. Okay, so this is the update for points where we don't make a mistake. Now the update for the points where we do make a mistake, so if we get this scenario, then in this case, the weight update is the previous weight multiplied by e to the power of positive alpha m minus 1. So what happens is we get exactly the same thing, except we don't get that negative. So this is just the square root of 1 minus epsilon over epsilon. So how do we make sense of these weights? Well, remember, HM is a weak learner. Okay, which means that the error rate it achieves is always going to be less than 0.5, right? Because a weak learner is just slightly better than guessing, meaning that the error rate always has to be at least slightly less than 0.5, which means that 1 minus epsilon is always going to be greater than epsilon. Okay, so what that means is that in this case, in the first case here, when we don't make a mistake, right, when the classification is correct, we're dividing a smaller number by a bigger number. So this number here is less than 1, right? Whereas when we are making a mistake, we divide the bigger number by the smaller number. So this number here is greater than 1, which means that when we make a mistake, so no mistake implies reduce the weight for point I, and then if you make a mistake, increase the weight for I. So the idea is that, the classifier made a mistake on these, didn't make a mistake on these points, so these points aren't that important for the next round, right? Because the next round focuses on the mistakes of the previous learner. So we want to look at the mistakes of the previous learner, give them a higher weight, and then retrain the model using the weighted loss function with higher weights for those mistake points. Okay, so that is the idea, right? The weights increase or decrease depending on whether the current learner made a mistake, and then the next learner is trained using this loss function here, right? This loss function here, where the weights are going to be higher for the points that the previous algorithm made a mistake on. Okay, so this might be a bit arbitrary. We're going to do a concrete example, but hopefully it's not. Hopefully the idea is kind of intuitive. Let me write out the pseudocode for the algorithm. So I'm going to use the same kind of notation as in the lecture notes, well, actually, I'll use H here. So let me explain what these are. So here, this is my data set. Here, this is the number of, well, actually, it's the size of the final algo, right? Because I want to create CMX, which is a combination of M base learners, and then this is the set of base learners. And this could be anything. It could be anything that's kind of a weak learner, anything that's kind of easy to train and quick to train. Okay, and then what we do is we initialize the weights at the start to just be 1 over n, where n is the size of the data. Okay, so let me, instead of writing n, let me just write the size of the data. So this means that we have a uniform weight. Okay, and that makes sense because when you first start, when you first start, you've got no information. You don't know which points are hard to train. So you just give everything an equal weight, and then you pick the classifier in the set of base learners, or the weak learner in the set of weak learners that minimizes epsilon 1, which is going to be equal to h1 not equal to y1. Okay, so it's going to minimize the rate. And by the way, the reason I'm calling this epsilon 1 is because if I sum over all the weights, right, the sum of 1 over d times d is just going to be 1. So the weights are already normalized. So I can just call the top part epsilon 1 because it's dividing by 1. But I'm going to pick the h that minimizes that weighted loss the weighted misclassification. Okay, and then I compute alpha 1 to be half of the logarithm of 1 minus epsilon 1 over epsilon 1. Then I update all the weights. Let's call this So for j in 1 to d, so I'm going to loop over all the data points. Okay, the updated weight for point I is going to be, well, let's look at our previous. It's going to be one of these two. Okay, it's going to be wi1 times the square root of epsilon 1 over 1 minus epsilon 1, if otherwise we're going to use the other update. Okay, so the first update, epsilon 1 over 1 minus epsilon 1, we use that if we didn't make a mistake. Okay, so if y1 equals to h1 of xi, and we use this one if, so yi rather, equals to h1, doesn't equal to h1 of xi. Okay, and then you repeat this, repeat for I equals 2 to m, okay, and obviously in the second step you use, so in the second step, in step 2, you pick h2 that minimizes epsilon 2, okay, which is now the weighted loss, but the weights here are based on the mistakes of the previous learner, right? And this should be over over the sum of the weights. So the point is that h2 is being trained on a loss function that minimizes the loss, a weighted loss, where the weights care more about the mistakes of the previous learner. Okay. So one thing that's left to talk about here is that this is slightly different to the derivation in the lecture notes. The difference is that this weight, right? The way I'm kind of updating the weights is not really giving me normalized weights, right? Remember at the start I said that, where was it? Was it at the very start? I said that sometimes we like to, or a lot of the time we like to do normalized weights. So what I'm getting here, what I'm getting in my current AdaBoost is a bunch of weights that don't add up to 1. So that actually doesn't make a difference for this algorithm, but I'm just going to go through and do the normalization just to show you that it's not a big deal, and we can update this algorithm to basically have the normalized update so that the weights actually do add up to 1 at every step. I'll just do that here. So again, this is not necessary, but let's just talk about it because I just don't want to, sometimes you see slight differences in the algebra and it looks like there's a big change, but I just want to clarify that there is no real big difference. So the goal is we want the sum of the weights at any iteration to be equal to 1, right? We don't have that at the moment, but we want this. So what is the sum? So by the way, how do we get this? Well, you take your current. So let's call my current weight updates tilde, right? And you just you basically just find the sum of those, okay? And you divide every single weight by the sum of the tilde weights, and then that's basically how you get a normalized weight, right? So here, what did we do to get the normalization? We took the sum of all the elements in the vector, and we divided each element by the sum. So in this case, the sum was 400 plus 96, okay? And now when I sum over this vector, the sum is just going to be 1. Okay, so the idea is not hopefully not too difficult to understand. So let's actually look at the let's look at our weight update. Okay, well, the way we defined the weight update was here, WIM is equal to WIM minus 1 times this guy. Okay, so before I say this, before I do this, we're assuming that WM minus 1 is already normalized. So we can always assume that the weights from the previous step are normalized because we start off with this weight, uniform weight, which is already normalized. So it doesn't make a difference. Like at W2, I can assume that W1 was normalized. So I can always assume that the step before me was already normalized. And I can write here WIM minus 1 e to the power of negative yi alpha m minus 1 h m minus 1 xi. Okay, I'm going to do the same trick where I'm going to break this up into two summations. Yi equals to hi, in which case I'll get e to the power of negative alpha m minus 1, and I'm just going to take it outside because it's not, it doesn't have an I in it, and this is the same trick as previous. And then here we'll get e to the power of alpha m minus 1 yi not equal to hi of wi m minus 1. Okay, now what is this? How do we simplify this first expression? Okay, so let me just note, what is yi not equals to hi? Well, this is just equal to the error rate at m minus 1, right? Because remember, I'm assuming that the previous weights are already normalized. So this this guy is equal to taking dividing by the sum from 1 to n of wi m minus 1, because this denominator, right, this guy is just equal to 1 already. So these two are equal, and we know that this is just equal to the error rate at m minus 1. So assuming this assumption of previously normalized weights means that this summation here is just epsilon m minus 1. So what is this guy? The sum of the correctly classified, well, it's just going to be 1 minus epsilon m minus 1. And this guy is just going to be epsilon m minus 1. Okay. So all I've done is replace the summations by the epsilon term, and we can do that because of this assumption that the things before are normalized already. And this is basically the number, and I think in the lecture notes we call this Z M. This is the number where if you divide each element of the weight vector by, you'll get a vector that is normalized. Okay, so this is our number 496 that we got here. Okay, and let's actually simplify this. Well, we know that alpha m minus 1 is equal to half log right? We know that this is equal to this. So if we plug this guy into the expression up there, okay, well, e to the power of negative of this is just as we did this already. This is just going to be the square root of epsilon m minus 1 over 1 minus epsilon m minus 1 times 1 minus. Okay, and then this e alpha m minus 1 term we did already as well, and we just get the reciprocal. Okay, now hopefully you see that the denominator here and this number here, they cancel out, except that this one is a square root. So what we get is square root of epsilon m minus 1 from the top term, and then we get a 1 minus epsilon m minus 1 term from the fact that this guy gets a square root term canceled out. And we actually get the same thing over here. Okay, and so what this tells us is that Zm is 2 times the square root of epsilon times 1 minus epsilon. Okay, so the thing that would change in our updates is instead of just taking Wi m is equal to Wi m minus 1 e to the power of negative yi alpha m minus 1 okay, so instead of just taking this to be our update, we now have an additional 1 over Zm term here. So let's go back to our updates here and see what that would change. Okay, well, let me see if I can copy this just to make life easier. Okay, so these were our unnormalized updates. So let's try to normalize them. Well, basically, we know that Zm is equal to 2 square root of epsilon m minus 1, 1 minus epsilon m minus 1. Okay, and let me just do the generic weight here. Let me make this Wim is a function of, okay, well, instead of making it too messy, I'm just going to rewrite it all out. Okay, this should be, so I don't want to just focus on the m equals 1 case. I want to focus on just the general m case. Okay, so the update for weight m is the previous update at m minus 1 times the epsilon term here. Okay, but now if I divide each one by Zm, okay, so what happens? Well, what happens if I take this epsilon m minus 1 term, 1 minus epsilon m minus 1, and I multiply it by 2 times, sorry, and I divide it by 2 times okay, this thing here. So what happens is that the epsilon m minus 1 term cancel out, and what I'm left with is 1 over 2, 1 minus epsilon m minus 1. Okay, so Wim is equal to Wim minus 1 times 1 over 2, 1 minus epsilon m minus 1. And so this is the case where yi is equal to h of I, so there's no misclassification. And in the other case, I'll leave it for you to work out, but it's just 1 over 2 epsilon m minus 1 if yi not equals to hi. Okay, so these updates are normalized in the sense that the final weight vector is going to be, if the sum of the weights is going to be 1, but it actually doesn't really change much. It actually changes nothing. You'll still get the same model either way. uh, but the one thing I did want to say is we talked about, we already explained these updates, right? So let's see if we have the same intuition for these updates. Well, when we're not making a mistake, yi equal to hi, then what are we doing to the weight? Well, we are 1 over 2, 1 minus epsilon. 1 minus epsilon is a number bigger than 50%, right? Bigger than 0.5. So this weight is becoming smaller, whereas this weight here is a number smaller than 0.5, so this weight is getting bigger. Okay, so we still have the same basic intuition of how we change the weights on the points. Okay, and as for everything else, in terms of this, in terms of the pseudocode here, it's exactly the same. All I've changed is this part here, and again, as I said, you don't actually need this change to make this algorithm work. And these are the updates from the actual lecture slides. So before we move on, I just wanted to note a minor mistake I made in the pseudocode. Okay, so here when I presented this pseudocode, let me call this the unnormalized version. Right, so these are unnormalized weight updates. So here the weight, I actually use the normalized weight. This is actually wrong. I mean, it's not wrong, but it's just to keep consistency. The weights here should just be uniform, 1. So not uniform, but just equal. Every data point gets an equal weight of 1. The reason is, if you look at the way we define the weight, let me just go to the definition. Okay, so here's how I define the weight. I define the weight kind of recursively, right? So what is, so let me just put it here, WIM is equal to e to the power of negative yi cm minus 1 xi. So so if you just want to keep consistency with this, the way I set up the model, what is wi1? It's e to the power of negative yi c0 xi, right? So what is the 0 model? It's just basically 0, right? We have to take that to be 0 because there is no model yet. So this is just e to the power of 0, which is just equal to 1. Okay, so it's not a big deal. It actually makes absolutely no difference, but I just wanted to keep the consistency here. So when we set up the unnormalized version, we can just set the weights to 1. And obviously, the normalized, if I have a vector of 1s, the normalized version of this is just going to be the vector of 1 over n, right? So it doesn't make a big difference, but I just want to keep consistency here. All right, so that is basically the idea of boosting. The thing I wanted to go through next was just a concrete example to try to illustrate these points and just kind of make them stick. So let me try my best to draw. So this is a toy example. Okay, and I basically want to look at a classification problem where I have x1 and x2, and I'm going to draw a grid. So x1 can ranges from 1 to 4, and x2 is just from 1 to 2. And I'm going to have a set of points. So let me put them positive points look like this, and negative points in blue. Okay, and just for clarity, I want to label these points A, B, C, D, E, and F. Okay, and the goal of this exercise is to build a an adaptive boosting classifier from the set of classifiers that I'm going to define. So this is going to look slightly weird, but I'm going to define these classifiers to be H11, H12, H13, H21, H22. And basically what H11 is the model x1 greater than 1, x1 greater than 2, x1 greater than 3, x2 greater than 1, sorry, x2 less than 1, and x2 less than 2. So what is, let me just try to explain what this is. Okay, so x1 greater than 1 is going to be positive if x1 greater than 1, otherwise it's going to classify as negative if x1 is less than 1. So on this toy data set, x1 greater than 1 is this line, just a straight line at x1 equals to 1, and anything to the left of it is going to be classified as a negative, and anything to the right of it as a positive, right? Similarly with x1 bigger than 2, it's just going to be this line that classifies everything to the right as positive, everything to the left as negative. And similarly for x1 greater than 3. And then on the other side, we have the x2 models. This is going to be plus 1, so this model is going to be plus 1 if x2 is less than 1, and negative 1 if x2 is bigger than 1. Okay, so for example, x2 less than 1 is going to be this model that classifies everything below it as positive and everything above it as negative. Okay, so this is like my set of base classifiers, which are really weak learners because, well, they're basically all going to achieve an error rate of, sorry, that's wrong. They're base learners because they're extremely simple. They need to actually be able to classify this data set, which needs a decision boundary that looks like this, right? But none of them are capable of doing that on their own. So they're really simple classifiers, and I'm going to combine them in a way such that we can actually learn this decision surface. Okay, so I've just made things a little bit neater with the grid, but hopefully it's pretty straightforward. We have 3 points in the negative class in blue, and 3 points in the right class in red, and I've labeled the points so you can refer to them. So we just start off with kind of round 1 of boosting. So the first thing is that we need the weight vector at the beginning. Okay, so the weight is going to be uniform, right? So we're doing this version of the algorithm where we have the normalized version, right? So we have a uniform weight, and these updates here, we're going to use the normalized version that we derived here in red. Okay, so first step is how many data points do we have? Well, we have 6 data points, so this is going to be a uniform weight for the 6 data points. Okay, and this represents the weight of A, the weight of B, the weight of C, D, E, up to F. Okay, so that's the first step. Then we want to choose a classifier. Okay, so choose, we'll call it H, sorry, and I don't want to confuse the labeling H11, H12 with H1, so I'll call this H bracket 1. So this is the first classifier to enter our model. And we want to choose it to minimize epsilon 1, which is the sum of the weights. Okay, the sum of the weights where we sum over the mistakes. Okay, so we just need to look at where's the classifier making a mistake. We take those weights and we add them up. All right, so let me show you exactly what I mean by this. Let's draw a table here. Okay, and here we'll put our model, and here we'll put the rate, the error achieved by this particular model. So the first model is going to be x1 greater than 1. So I'm just rewriting these models. So it's not the best notation because this is kind of just a condition and not really a function. But hopefully it's kind of clear what this thing does. So okay, what does this model achieve in terms of error? Well, let's just draw it again in red. Well, not in red, maybe in a different color. Let's say green. All right, so x1 greater than 1. Here's x1 equals to 1. Again, it's saying anything to the right of this line is going to be a positive point, and anything to the left is negative. So it makes a mistake. So it classifies A and B correctly. It also classifies D, E, F correctly. It only makes a mistake on C. Okay, so this mistake here, yi not equal to h of xi, is only happening at a single point. So we only have one term in this summation, and that term is going to be the weight of the point we're making a mistake on, which is point C, and which just has a weight of 1/6. Okay, so actually before I do that, let me get rid of the boundary, so 1/6. Okay, hopefully this is pretty clear, right? We're just making one mistake with this model, and so the error rate achieved is 1/6. How about the second model, x1 bigger than 2? Let's do them all, just for clarity. Okay, so x1 bigger than 2. Okay, well hopefully see if I put a line here, it's classifying the points on the right as positive, so these two are correct. Classifying the points as negative on the left, so these 3 points, the A, B, C points, are correct. It's only making a mistake at D, so again, this has an error of 1/6. Okay, how about x1 greater than 3? So this would classify everything to the right here as positive, so it's not making a mistake on E, and everything to the left is negative. So D and F are both mistakes. So now we have two terms in our summation, and their weights are 1/6 each. So 1/6 plus 1/6, so 1/3. Keep forgetting to erase the boundary, so 1/3. And next we have x2 less than 1. So x2 less than 1 is this boundary, right? Is everything below is positive, and everything above is negative. So this one is making a mistake on points D and E, right? Because it's classifying them as negative. So again, it achieves an error of 2/6. So 2 mistakes, or 1/3. And finally, x2 less than 2, well, that hopefully you can see is also going to be achieving an error of 1/3. It's going to make 2 mistakes if we put a boundary there. Okay, so in this really simple case, I've only got 5 hypotheses, 5 models to choose from, so I can explicitly compute the error on each one and just pick the minimum. So here I've got 2 candidates for the minimum, this one and this one. They both achieve the lowest rate. So I'm just going to pick just the first one. It doesn't really matter because it's a tie. So I'm going to pick this model. So my H1 model is the model x1 bigger than 1. And maybe I'll just put this in brackets just to make sure that we know that this is actually a function that tests this condition. Okay, so that's the first step, well, second step after we pick the weights. So what do we do next? The next thing we do is, well, the model is going to be a weighted combination of classifiers, so we need to pick the weight, right? So what is alpha 1? Well, we just use our equation that we derived before, so it's going to be half log 1 minus epsilon 1 over epsilon 1. And when I say epsilon 1, I mean the rate achieved by that classifier that you chose. So the rate is 1 over 6. So this is going to be half log 5 over 6 over 1 over 6, which is just half log 5, which is, so I just computed it earlier, it's 0.8047, but I'm just going to call it 0.8, okay? 0.8. Don't do this if you're actually building this model. I'm just going to do it here because I don't want to make my life too difficult, and I want to try to just illustrate the concepts rather than go for perfect accuracy. All right, so that's the weight. What's the last thing to do? Well, it's update the weights. Okay, so update the weights. Okay, well, we know that there's two kinds of updates. The kind of updates for points where we didn't make a mistake and points that we did make a mistake. So let's do the ones where we didn't make a mistake. There's 5 of them, right? We didn't make a mistake on A, B, D, E, and F. We only made a mistake on C, right? So everything else here is not a mistake. So for these points, the weight, the second weight, is going to be the initial weight times 1 over 2, 1 minus epsilon 1, right? This is the update that we derived. This is the normalized update. So this is going to be 1 over 6 times 1 over 2, 1 minus 1 over 6. Okay, and this is going to be just 1 over 10. So you see the weight went from being 1 over 6 to 1 over 10. So the weight is actually going to be smaller. And the reason is that we classified those points correctly. So we want the next classifier, right? The classifier is tries to minimize this. It tries to focus on the points that the weights kind of dictate what the first model focuses on. So when we change the models, when we change the weights, we want the next model to not focus on these points as much. Okay, so what about the update for C? Okay, we're going to have the same update. We're going to have the same update that we had before, so 1 over 2 times epsilon 1. So again, so these are the points where no mistake. These are the points where we made a mistake. Okay, now this is going to be 1 over 6 times 1 over 2 times 1 over 6, and this is just 1 over 2. So you see this weight now is much bigger. It used to be 1 over 6, now it's 1 over 2. And note that the weights actually, well, let me rewrite the weights here. So W, this is my W2 vector. I'm going to have 1 over 10, 1 over 10, 1 over 2. Okay, so these are my points A, B, C, D, E, F. Now, you should note that the sum of this weight vector, so 1 over 10, there's 5 1 over 10s, so that's half plus half is just equal to 1. So this is a normalized weight vector. Before I continue here, I just wanted to note one thing that I skipped over. I just want to add a step here in the middle before we do the weight update, which is define the model. C1 is equal to 0.8 times H1. Okay, so now we have our model. I just want to show the incremental, as we go through the steps, we add more and more models to this thing. So this is our current model. Okay, back to updating the weights. So now we have these weight updates. So let me redraw the points, but I want to do it in a way such that the size actually tells us the weight. So you'll see this kind of commonly. So you'll see I'm going to draw them smaller, and the reason is that these points actually are now weighted less, and I want the size to reflect the weight. So C is going to be a larger weight, right? So this is how you'll see it usually in a lot of examples. You know, if you Google this, you'll see this kind of you know, showing the weight of each point, showing the important points as the larger points. And let's see if I can get this right. Okay. Okay, and this is just kind of graphically a nice way of just representing, you know, the stuff that we are, you know, the weights in kind of a graphical way. Let me see how to get rid of this. Okay. All right. So so we see here that, you know, here are our positive points, and here are our negative points. Okay, but you see that the next classifier is going to focus more on that point C, right? Because misclassifying C, you're going to pay a much higher cost than you did before. All right, so now we do round 2, and again we just start all over again. We you know, we pick H2 that minimizes epsilon 2, which is going to be, again, yi not equal to h2 of xi times the weight, and the weight now is obviously the weight in the second vector, w2. Okay, so let's just do it all over again. I know this is kind of slow, so you can skip through it if you're comfortable with the content, but I'm going to go through it really slowly because you know, I want to be crystal clear. There's a lot of moving parts, and it's good to work through it. Okay, so again, we have our 5 models. Okay, now let's look at x1. So this was our previous best model, or one of our 2 best models. Let's see what it does now. Well, again, it's going to misclassify the same points, right? It's going to misclassify everything to the, it's going to misclassify that C because it classifies everything to the right as a positive. So again, it just makes one mistake, but that mistake is really expensive now. So this guy here, yi not equal to h1 of xi, sorry, h11, this model here, h11, is equal to the point C. So the cost is the weight of C, right? So the cost here is going to be half. Okay, so this is the idea of boosting right here. The weight has given us a change in the way we look at the models. This model used to perform. So let me draw a better half than that. Okay, this model used to perform really well when they all had uniform weights. Okay, but now that we've changed the weights, it's going to do quite poorly. Actually, it's going to get a error rate of 50%. In fact, it's not even a weak learner anymore. It's worse than a weak learner. Okay, what about x1 bigger than 2? Well, x1 bigger than 2 is this boundary here, and this one now is just misclassifying the point D. The point D has a weight of 1 over 10, so the weight here is 1 over 10. How about 1 over 10? How about x1 bigger than 3? That's going to still make 2 mistakes. So x1 bigger than 3 is going to make 2 mistakes. It's going to make them on D and F, each of which have a weight of 1 over 10. So this is going to be 2 over 10. And then x2 less than 1 is going to make a mistake on, so x2 less than 1 is this. It's going to make a mistake on D and E. So again, 2 over 10. And x2 less than 2 is also going to be 2 over 10. Okay, so now it's pretty clear that we have only one model that is optimal. Okay, so it's this one. All right, so let me write it here. H of 2 is going to be the model x1 bigger than 2. Okay, and okay, so that's our first thing. We picked the model. Now the next part is pick the weight for that model. It's going to be half of log 1 minus epsilon 2 over epsilon 2. So that's half of log 9 over 10 over 1 over 10. And this is going to be approximately just 1. Okay, and yeah, I'm going to take the weight to be 1. That makes life much easier. And now I have my new model, C2, which is alpha 1 H1 plus alpha 2 H2, which is 0.8 times the model x1 bigger than 1 plus plus 1 times, sorry, this should be 1.1, my mistake. So this is 1.1 x1 bigger than 2. Okay. Now, what does this model actually mean? So actually, let me make it really neat. Okay, so what does this model actually mean? It means that we can use C2 as a classifier. So let's take C2 of XA. So this, what does C2 say about this point XA? Well, it would say that it's going to be a combination of the classes that are assigned to it by each of these models. Okay, well, it's going to be 0.8 times, what does the first model classify point A as? Well, it classifies it as a negative point, right? Because it's to the left of the boundary. So this is going to be 0.8 times negative 1. Okay, plus 1.1 times the class that x1 bigger than 2 classifies it as. Well, x1 bigger than 2 classifies everything to the left as negative. So this is going to be negative 1. Okay, so this is going to be minus 0.8 minus 1.1, so minus 1.9. And because this is a negative number, remember our our classification is the sign of C2XA. So this is just going to classify that point as negative. Okay, so you see that it's making it's classifying this point correctly, right? The combination of these two classifiers in this particular way classifies point A correctly. What about C2 of XC? Okay, so that was the point that we made the first mistake on, right? Well, it's going to be 0.8. Well, XC is, so for the first model, x1 greater than 1, right? We know that it's going to classify C as a positive point. So it actually classifies it as a positive plus 1. But then the next model, x1 bigger than 2, right, classifies C as a negative point. So this ends up being 0.8 minus 1.1, which is negative 0.3. So the class is going to actually negative, which is correct. So you see here that the combination of the two models actually was able to classify C correctly. And note that the weight here, 1.1, is bigger than the weight 0.8. And the reason is the error achieved by this model is 1 over 10, whereas the error achieved by the first model is 1 over 6. So obviously the weight is going to be higher for a lower error model. And we actually get this decision being kind of overridden by the second model, by the addition of the second model. Okay. What about another point? Let's look at XD. Okay, well, D is going to be classified as by the first model, it's going to be classified as a positive. But the second model classifies it as a negative point, right? Because the second model is here, right? And it classifies everything to the left as negative, so here we get this, and so now we get negative 0.3, which classifies it as a negative point. Now clearly this is incorrect. So our model is still not finished, right? We haven't converged because we're still making mistakes on the training data. All right, so that's, I mean, this you don't need to do this, but I just wanted to illustrate what does this thing actually mean. And then the next step is how do we update the weights? Let me do that here. Okay, well, so non-mistake points, and then I'll do the mistake points down here. So non-mistake points, well, this model x1 bigger than 2 only makes a mistake on only on point D. Okay, so let's do, I want to do A, B, E, F. These are non-mistake points. The reason I want to do these and not C as well is that C has a different starting weight. So I just want to leave it on its own. So for A, B, E, F, WI3 is going to be equal to the old weight, which is 1 over 10, times 1 over 2 1 minus 1 over 10, right? 1 minus epsilon 2 is 1 over 10. So these weights end up being 1 over 18. Okay, so A, B, E, F get weight 1 over 18. What about C? Well, for C, WI3 is, well, the starting weight is not 1 over 10, it's half, right? Okay, so 1 over 2 times 1 over 2 times 1 minus 1 over 10. So this weight here is going to be now 5 over 18. So you see how they both get reduced by the same factor, but because the weight of point C was higher to begin with, we end up with a slightly higher weight than the others. And then for the mistake point D, well, WI3 is equal to, well, the starting weight of D is 1 over 10. So, and then we multiply by 1 over 2 times epsilon 2. Okay, and this is just 1 over 2. So you see the weight of D gets kind of pushed up. All right, so let me copy this. Okay, and let me erase all these guys just so we can reuse the figure. Shouldn't have left the boundary on this. Okay, so I want to draw. Well, let me first draw the write down the vector W3. So this is going to be 1 over 18, 1 over 18, 5 over 18, 1 over 2, which is, let me just write that as 9 over 18, so we can keep everything consistent. 1 over 18, 1 over 18. So now the classifier is really going to care about these 2 points, okay? And if we draw them again, D, I won't do the nice drawing now because I think we all get the point. D is going to be like this. E and F are going to be really small, so 1 over 18. And similarly with A and B, they're also going to be really small. Okay, and C is going to be slightly, well, not slightly, slightly smaller than D. Yeah. Sorry, these actually should all be just negative points, right? Okay, C gets a bigger picture because it's 5/18. Okay, and we have our boundary here. All right, so what happens now? So this is round 3. So we pick H3 to minimize epsilon 3, again, yi not equal to h of xi of wi 3. Okay, so this classifier, the choice of this classifier focuses really a lot on these 2 points. We could, we could do the table thing again, but I'm going to skip that. Well, actually, let me write it down, but I won't talk through it. I'll just give you the answer, and you can work through it in your own time if you wish. So we have our okay, and we end up getting 5/18, 9/18, 10/18, and 2/18. Okay, so maybe we'll just walk through one. X2 less than 1 is this boundary here. So anything above it is going to be negative. So it's making a mistake on D and E. So D is 9/18, E is 1/18, so together they're 10/18. Okay, and it turns out that X2 less than 2 is the best model. Okay, so H3 is equal to the model X2 less than 2. And next thing is to compute alpha 3. Which is equal to 1.04, which I'll just take to be 1. Okay, and so now our classifier, let me write it here, C3 is equal to 0.8 x1 bigger than 1 plus 1.1 x1 bigger than 2 plus 1.0, well, just 1, sorry, times x2 less than 2. Okay, so this is our model now. We have 3 classifiers. And let's actually see, let's see how this performs on all the points. So I'm going to compute C3xa, xb, c, and f. Okay, and this is going to be a little bit tedious, but I just want to go through it. So we're going to have 0.8. We're going to have the same. Let me, yeah, I think this will make it a little bit easier to understand when I write everything out. Okay, and finally, the third classifier is going to have just some 1 times something, the classification of that model. All right, so let's look at XA. So what does x1 bigger than 1 do? It classifies all the points to the right as positive, all the points to the left as negative, so it makes a mistake only on C, right? So it classifies A and B as negative points, it classifies C as a positive point, classifies D as a positive point, and E and F as positive points, okay? What about for x1 bigger than 2, the second model? Well, that's this model. and it classifies everything to the left here as a negative point. And it classifies everything to the right as a positive point. Okay, and finally, what about x2 less than 2? Well, that's this one. So that classifies everything below as a positive and everything above as a negative. So it makes a mistake on, sorry, it classifies A, C, and E as negative points. So A, C, and E as negative points, and everything below, so B, D, F, as positive points. Okay, and let's see what we get here. So these are all negative classifications for A. So this is going to be negative 0.8, minus 1.1, minus 1. So that's going to be minus 2.9. So the classification is going to be negative. Okay. For this point, it's going to be minus 0.8, minus 1.1, so minus 1.9, plus 1 is minus 0.9, still negative, so we still get a negative classification. For point C, we're going to get 0.8 minus 1.1, so that's negative 0.3, minus 1, negative 1.1, so that classifies as negative. For these points here, so 0.8, so you can see that here this is going to be a positive number, so I'll just write down the classification, right? It's obviously going to be positive here, and here, and here. So what is this correct? Well, obviously negative 1 for these three is going to be correct, and positive 1 for these three DEF is going to be correct. And what this means is that we've completely learned the function, the boundary between these two. And actually, if you go back to the original space here, right? I said that none of these functions on their own could learn this, right? Because they're all linear functions, straight lines, and you needed something that was kind of zigzag through the grid. So on their own they couldn't. But if we look at the, let me do it in bright green. If we look at the C3 boundary, well, it's classifying them all correctly, right? So it means that the boundary is going to look something like this. Okay, which means that everything on this side is positive, everything on this side is negative. And that's really the power of boosting. It's we have these really simple models, right? These are kind of trivial models, but if we use enough of them and we combine them together in a smart way, we can learn these really complicated. I mean, this is not too complicated, but for this particular class of functions, this is a complicated boundary, and it kind of goes back to this idea where, I think I drew it at the start. Here, we have a complicated function. We can use lots of simple functions to kind of approximate the more complicated function. Okay, and you can see here for this kind of simple example that we were able to do it in 3 steps. Okay.